So in this video, we're going to take the things we've learned about the two-dimensional world. That's what we've been dealing with so far. Everything has been sitting in the XY plane, and we're going to look at how we can translate those lessons into three-dimensional shapes. And there's a lot of three-dimensional shapes that we have formulas for, like we've got this rectangular box down here. It's got a length and a width and a height, and we know the formula for the volume of that. It's length times width times height. But the question is, how can we kind of think about what we know about calculus and the shape, and so that we can maybe find the volume of a shape like this kind of crazy guy over here, something that we don't have a nice closed geometric formula for. So let's start with this idea here of, say we have this rectangular box that's got a length of 9, a width of 3, and a height of 6. So what we could do is take this box and take the length and chop it into 9 pieces. And I'm doing that so each piece has a width of 1, kind of like slicing a big loaf of bread. And then what that's going to do is give us these little slices here that are going to have, draw my picture here, they are going to have a width of 1, or width of 3, excuse me, a height of 6, and then a length of 1. And we could do that for all 9 of them, and our volume would exactly be, that area of sort of the face of this here times our length. And we would do this for all 9 of those rectangles, and that can give us the volume. So it's the area of, sort of the front of that slice times how thick that slice is, add them all up, and that would give us the same volume as if we just did that, which we know we also could do. So that's the idea of what we're going to do with these sort of goofy shapes. We're going to look at what happens if we make a slice of it, and we look at the area of the front of that slice and then multiply it by how thick we make that slice. And if we have, however many slices and we add them up, then that's going to give us our volume. So the idea here is that we're going to take our crazy shape and, just like before with that rectangle, slice it like a big old loaf of bread. Now, just like with our areas, if we make those slices skinnier and skinnier, we're going to get a better approximation to the volume. But for all 3 of those figures, what we're finding is the sum from I equals 1 to n. And I'm sorry that down in my definition here it has a k. I kind of stole it from a different book, but it's the same idea whether you call it I or k. And it's going to be the area of, that front part of each of our slices times that thickness of our slice. And so we've got the area of each of those individual fronts times then how thick they are, and that gives the volume of that slice that approximates our volume overall. So if we take the limit as n goes to infinity of this, so again making more and more smaller and smaller slices, that's going to eventually get us to the shape that we want. And if you look at this, that is an integral. We've seen these time and time again. This is going to be the integral from a to b of whatever that area function is, so that face of our slice, and then delta x always turns into dx. So let's do this method on a shape that we know what the formula is. So we're actually going to use calculus to prove this formula. So we're going to look at a right circular cone. So we're going to get to see Sarah draw a picture here. Not always the best artist, but we know that the volume of a right circular cone is 1/3 pi r squared h. I did have to look that up. That was not one that I have memorized, but that's the formula. And this is one that, you're just told, here's a formula. And then the question is, where does this come from? So a right circular cone looks like this. And so the height that we're talking about is from the base, which is a circle, up to the top. so up to that highest point made with a right angle with our base, and then the base has a radius. So what we're going to do is we're going to take this cone and we're going to adjust it here. I'm going to try to draw my axis a little bit straighter there. We're going to turn it on its side so that the tip of the cone or the top of the cone is at 0, 0, and then it kind of goes out along our x-axis there. So if we go all the way out here, it's gone all the way h units to get to the end, and then that's our radius. So the idea here is what we're going to do is we're going to take slices of this cone and find the volume of our slice. So, oops, sorry, it keeps being the eraser. So here's our slice. So the thickness of this slice is delta x. That's our change in x. And then we need to figure out what the area of the front of this slice is. And the front of the slice is a circle. So we need to know what that radius is. So maybe we'll call the big radius radius 1, and this little radius, we'll call this radius 2. Well, we can use similar triangles to figure this out. So, and actually, instead of calling that radius 2, I think maybe we'll call that y. That's going up to some y value. It's starting at the x-axis and going up to some y value. And we could also talk about maybe a little cone that we're making here with our slice as the base, and it's got a height, a height of x. And then we can use similar triangles. So we've got two similar triangles here. We've got a little, let's get a highlighter that's a little bit easier to see. So we've got a little triangle right here, and then we've got a bigger triangle. And those two triangles are similar triangles. So we can set up the relationship that y over x is equal to our radius over the height. And you can set up these proportions in, sort of slightly different ways, whatever you need them to be. And we can multiply both sides by x. And so what this does is it gives us a relationship between that little cone that we made, the little pink cone, and then the big blue cone. Because with this big blue cone, we would know what the radius and the height are. Those would be fixed. And so the area of the front of this slice is equal to pi times the radius of that slice squared. Well, the radius is this y value we have right here. And I'll get out that y value, and that y value is equal to our big radius divided by our big height times x. So how far we went out on the x-axis. So pi times our hx being squared. That's our radius. So our integral is going to go from 0 to our height, because we're looking at the x-axis here. How far did we go on the x-axis? And we went as far as the height of our cone. So it started at 0 and goes all the way to the total height. And then we've got our area function, which is pi r squared h squared x squared. So that's just taking our area function and squaring everything. And then our dx. Now with this, there's a bunch of constants in this. Pi and that r squared over h squared, those are constants. Those things are fixed in this cone. So we've got pi r squared h squared. We can pull all of that outside of our integral. And then we've just got x squared inside of it. So it's actually pretty easy. We've done these a lot before. We get 1/3 x to the third. And this is going to go from 0 to h. Then if we do our fundamental theorem of calculus, we've got 1/3 times pi r squared h squared times h to the third, and then minus 0. That's what we're going to get from plugging 0 in. And if we look at what we've got right here, We've got h squared on the bottom and 3 of them on the top, so that leaves us with 1. And if you look at what we're left exactly with 1/3 pi r squared h, which is that volume formula that we were given.